Hey guys, very good evening everyone and welcome to another session by 360DigiTMG. We have been discussing about the series of domain analytics and we have been seeing about sports analytics in particular since yesterday. Yesterday we discussed about the introduction about how can one get benefited by sports analytics and what are the various things or traits that are required to become a sport analyst. What are the tools and tricks you need while you are working on the analytics related to the sport? But guys, whatever it may be, whenever we talk about data science or whenever we talk about working on a project, we need a methodology to work upon. Now, when we follow this methodology, it ensures that whatever project we are working upon, as in when we relate this methodology to a sports analytics. So you collect the data, you clean it, you apply machine learning algorithms, and you get some prediction. A particular methodology needs to be followed whatever the project you are working on. And the most in-trend methodology that as a data scientist we are using these days is CRISP-MLQ, that is cross-industry standard process for machine learning with quality assurance. Today we will be discussing about this methodology and few other things besides that. Moving ahead, guys. So today's agenda is going to be your stages of analytics. What is CRISP-MLQ methodology? We will understand about that. We will also see inferential statistics and supervised and unsupervised learning. What is the basic difference? How does the data split happen? What are the error functions that you get? And what is overfitting and underfitting in a model? These are going to be our today's agenda. Okay. Talking about the stages of analytics, it has four stages. The first stage is your descriptive analytics. What happened in the past, right? How much did the player score in the past? How much the player scored in the past? What injuries occur for that particular player? When you talk about past, what were the preventive measures taken to boost the performance of that player? Diagnostic. When we talk about past, that is covered into your prescriptive analytics and diagnostic analytics. Descriptive, as in injury happened to a player, how that injury happened, what were the effects of it, how much time did he take the player took to recover. Diagnostic. Predictive analytics and prescriptive analytics. These two stages talk about the future. So here, not only past, we are also talking about present. And in predictive analytics and prescriptive analytics, we talk about future. A person who talks about your past and the present is regarded as your data analyst. A person who talks about the future is called as your data scientist. But a data scientist is also deemed to have the knowledge of working on past and present time. So a data scientist is a full package, a person who can talk from past to present in your future. Now, coming to our project management method, CRISP MLQ, cross industry standard process for machine learning with quality. What happens over here is this particular methodology is having 6 phases. The first phase is your business understanding. You take the data from the data source, so whatever it may be, primary or even before taking that. When you start working on a project will be given to you by your organization or by your client. So as soon as you get hold of a project, a business problem will be given to you. Based on this business problem, you record your business objective and constraint. Constraints are the stipulations that will be put on you while achieving this business objective, which will help the client to solve this business problem. Right. In the second phase, once you are done with the understanding, business problem and recording your objective and constraint, you venture into your data understanding. I mean, we are a data scientist. We need some data to work upon, right? So you start collecting the data. And primarily, there are 2 sources of data collection. One is your primary data source, and one is your secondary data. Now, the thing is, when we talk about primary data source, this data or the data which you collected from this data source will contain the exact information that you need to solve your business problem. But the drawback over here is it is very costly and time-taking. As your feedback form, your survey. Suppose you want to collect feedback from, say, 20,000 people. Imagine you hired 5, 10, 20, or maybe 50 people. Imagine the amount of time. Imagine the amount of money you would invest to get hold of the data from these people. Very costly and time. But you will exactly get the information that is. As the feedback form you are taking, it will actually contain the questions that you need to solve a business problem, right? And people are answering to that question. So you are exactly getting the information that you need. But that is a drawback of primary data source, costly and time taking. Whereas when we talk about secondary data source is easily available. Right. But the drawback is that though it is easily available, it may or may not contain the exact information that you need. So you will need to work upon that data. As in you want to say make a curtailed tariff plan for a company, telecom company, say J. So you went to the, various data sources and you got hold of a tariff plan of other competitor telecom company, say we. Now this is a secondary data. Though both are tariff plan, but you are not getting hold of the exact information that you need to solve your business problem for this plan. So the data set that you got from this, competitor company, you need to work upon that and you need to prepare that. In that way, you're going to solve your business problem. That is your first. Second stage is nothing but your data preparation. Now, as we know that the data that we collect from the secondary data source may or may not contain the information that we need. So we need to prepare it. It will also contain a lot of ambiguity. It will also contain a lot of missing values. Duplicate values will be here, right? Outliers will be there. Now, all the things in your data set that is only going to hamper your analysis, right? So the data that you collected over here in secondary data source, you need to prepare, clean, right? And then you venture into your model building in the third phase. You apply various clustering techniques. You apply supervised learning, unsupervised learning. You get the analysis for each of them. You compare them. All these things. Tuning again and again. Say you made a model and you are running it on the data set. It is giving you various accuracy, but you are not getting the desired accuracy of the result. So you keep on tuning your model until and unless you get your desired accuracy. And then model evaluation. When you are fully satisfied with your model, you deploy that. And once your model is deployed, say after 6 months or 8 months, you monitor that model and you keep on providing the maintenance for the client. All these things are. So these are the 6 stages of our project management methodology called as systematic that you need to follow while working on any project. Now, when we talk about model building, we have supervised learning and unsupervised learning. But the catch over here is that the world that we live in, the amount of data that is being generated is being generated, 80% of your data is unlabeled data. Whereas only 20% of your data is labeled data. When you have the unlabeled data, unsupervised learning needs. And this is how your model works. You take the historical data. Here we are training the data. Here we are training the model. So this is how the training happens for a model. You take the data and you pass it to your machine learning. So let me give you an example. Suppose you have a cluster like this. It is having various images of cats and dogs. Not a cluster. Suppose we are having a database. Various images of cats and dogs. Now, when you apply your unsupervised learning, it will form 2 clusters. This is cat and these are dogs.
Excuse me, sir, sorry to interrupt.
Yeah.
Can you share your screen, sir? It's not visible if you are.
Screen is not visible. Oh my God. Just a moment. Just a moment.
I thought
Why
you
are
were
you
not.
telling so late?
I thought you were not. I mean, sharing the screen. So, and Chris
Oh
Pamel
my
was.
God. Just a moment. That was a very big blunder. Huh? Sorry, Raksha. Yeah, now it is visible.
Yes, sir.
Oh, so again, coming to the topic that we were discussing. So we have a data which is having a lot of images of particularly cats and dogs. But this is unlabeled data. So what will happen over here is that when you apply your unsupervised learning, it will form two clusters. And one cluster will be having the images of cats, one cluster will be having the images of dogs. So what happened over here? Your machine learning is not having any label data, just based on the pattern it is doing the cluster. So this is what happens over here. You get your historical data, machine learning, works on it. You pass it to the machine learning, and based on that, you get some patterns. Some patterns you are getting. This is how you train your data. When you are fully satisfied, you take the new data that is the data given by the client, and you use your rules and patterns on that, and you get the prediction. Whereas in supervised learning, you take the historical data, you apply a simple random sampling over here, and then you split the data into two parts. One is your training data and one is your validation. You take the training data set, pass it to the machine learning, and you will get a mathematical equation. We got a mathematical equation. This is nothing but a model. You take this mathematical equation and make your validation data set, which you have split it from here, and you get your prediction value or your validation value. Now, once you are satisfied with it, that is fine. But if you are not satisfied with your, outcome, again you go back here and again you train more data. Again, you keep on training your model unless and until you are fully satisfied with your validation. Now, once you are satisfied with it, use that mathematical equation on the new data and you will get your required prediction and outcome. This is how the things happen in the supervised and unsupervised learning in machine learning. Machine learning, there are two groups. One is the supervised learning and unsupervised learning. And this is how your data split happens, guys. You have the data with you. You split the data into three parts. Training data, validation data, and testing. Training data, you keep validating and keep retraining the model until the desired accuracy is achieved. And then you build a model. Now this training is being done on the training data to get the training error and the accuracy. Once you have the model, once you are fully satisfied with the accuracy, you build a model and then you use that to test on the validation data to get the validation error and accuracy. Then you fine tune the model parameters to get the better. And what happens is when you build a model, you build various model, model 1, model 2, model 3. Every model will give, different accuracy and error. Whichever is giving you the least error and the best accuracy, you choose that. And then you take the model and you check it on the testing data. Test on the testing data to get your test error and accuracy. This is also called as a generalization method. And then you check for your model overfitting or underfitting. What is this video? We should run this multiple trials and take average or take the majority. We also combine your training and validation data to run the model, which has given the desired result based on a set of finalized model parameters. Then you test the model on your testing data. We also ensure the model neither overfit, that is the variance, or underfit, that is the bias. What are these things we do? Now, coming to the error function, also called as your confusion matrix. Now, suppose your Y is category, as in this case, disease present or absent. Category. So, what is the confusion matrix? That is the question. Confusion matrix, guys, is a table that is used in classification problems. To do what? To access whether errors in the model were made. The rows represent the actual classes the outcome should have been true positive, true negative. True positive, false negative. While the columns represent the predictions that we have made. Now, what does the confusion matrix tell? The confusion matrix, we use it to define the performance of a classification algorithm. Now, confusion matrix, it visualizes and summarizes the performance of a classification algorithm. All right. Just let me throw more light on this. Okay, yeah. One more thing. What happens is when you do the predictive analytics, say you recall or say specify or say accuracy. When you are doing your predictive modeling or say your precision, confusion matrix is very useful because they give the direct comparison of values like true positive, false negative, and true negative. When we have say two class problem where it is very easy to understand but can easily be applied to say problems with 3 or more class values by adding more rows or columns to the confusion matrix, that is where you should use your confusion matrix. How do we calculate the confusion matrix? That is also a problem. That is also a question. So here we are having disease present, disease absent. This is a category that we are having. And true positive, true negative are the actual thing. When you want to calculate the accuracy, the formula for calculating your accuracy is true positive plus true negative. True positive is nothing but in this case, whether the disease is present or absent, a patient with disease is told that she has a disease. True negative, patient with no disease is told that she does not have the disease, divided by the total summation of true positive, false negative, false positive, and true. In this way, you will get your accuracy. Talking about the error, the formula for calculating your error is false positive, false negative summation divided by summation of true positive, false negative, and true. That is how you calculate your confusion max. And again, here all these things are given related to the disease table that we were seeing earlier. So precision, that is nothing. You also calculate the precision I was telling you, right? So precision is nothing but your true positive divided by true positive plus false positive. This will give you the probability of correctly identifying the random patient, precision, with disease as having disease. You can also calculate your sensitivity. That is nothing but your recall or hit rate or true positivity. Specificity, false positive ratio. All these things you can, make up when we are talking about confusion math. All these functions are. And when you have the continuous data, then we have these functions: mean error, mean absolute deviation, mean squared error, the formula over here, the root mean squared error, mean percentage error, mean absolute percentage error. So you are having your actual data over here. That is your 100. You know that. And then you started building a model. Suppose forecasting model you are making. You made a forecast based on the model 1. And that model predicted 101. Now, if you compare this and you compare this, the error is 1 over here. That is for your 1 model. When you do the forecasting based on the second model, you get the value 110 over here. Oh my God. Compare this, the error is 10. Now, obviously, you are going to choose this model, right? Or you are even going to fine tune it more and more. See, in the data science, or when we talk about building this model, no one can achieve 100% accuracy. That is for a known fact. No one can achieve that. And if someone says that, you know what, I will make a model and that achieves 100% accuracy, then that guy deserves a Nobel Prize. As simple as that. No one can achieve 100% accuracy. But the various accuracy that you are achieving, you choose the best model which is giving you the best. As simple. Formula for calculating your, okay, not formula. When you take your total percentage of accuracy and error percentage, and when you take the summation, it will always be equal to 1. And even when you take the percentage, it should always be equal to 100%. That is the thumb rule that you need to hammer in. And then we have something called as a model evaluation. When we talk about model evaluation and tuning, when we talk about model evaluation and tuning, there are two terms that you will be coming across a lot. That is variance and bias. Variance is nothing but your overfitting. Bias is nothing but your underfitting. Now, overfitting is when the model's error on the training set is very low, but the model's error on your test data is large. Let me summarize it over here. On your training data, the error is low. On your testing data, error is when we talk about overfitting. Underfitting is when the model's error on both your training and your testing data is very high. On that is the simplest way I can, tell you the difference. Other way, if I were to say, underfitting means that your model is actually, accurate, but the predictions that will be happening over here, that will be incorrect prediction. In underfitting, sorry, not in overfitting. In underfitting, the model is right, but the predictions that you are making, that will be incorrect prediction. Whereas in overfitting, it means that the model that you made is not making accurate prediction. Underfitting, guys, occurs when our machine learning model is not able to capture the underlying trend of your data. To avoid your overfitting in the model, the feed of training data, it can be stopped on your early stage. Due to which what will happen, the model may not learn enough from your training. But the question is, how do we fix this overfitting? When you want to fix the overfitting, you might want to consider few factors, as in, say, you might want to reduce features. Variance is more. You might want to reduce the variance, that is, reduce the feature. That is a quite obvious, way that you can do that. Another way is model selection algorithm. You can select model selection algorithm, or you can feed more data. You should aim to feed data enough to your model so that the models are trained, tested, and validated. And then you regularization. There is something called as regularization. You might want to consider that. A few other things that I would like to tell you. Okay. Coming back to our, for a balanced data set, we have been discussing about choosing your training data set. Whenever we have a data set, we are going to split it into training, validation, and testing data set. But how should we choose that? Or how should we, split that? Split randomly to avoid the biasness of. Take 60% in your training data, 20% in your validation, and 20% in your testing. Now, these numbers are, mostly what we follow. But again, this is not fixed. This is not fixed. Based on, say, your chief data scientist, or, say, your head of analytics, they can, tamper with this kind of percentage value. That is absolutely fine. But this is how you should choose your balance. And then you take 80%, that is your training and validation for training. The model you get over here, use that for testing. Large test set, 80%, ensures that estimate future error as accurately as possible. Or when you are having large training set, it will estimate your better estimate. Yeah, making sense? So that was about your overfitting or your underfitting, variance of bias. Again, if I were to repeat it, bias is nothing but assumptions made by a model to make a function easier to run. It is actually nothing but your error rate of your training data. When the error rate has a high value, we call it high bias. And when the error rate is low over here, we call it as low value or low bias. Variance, the error rate of your testing data is called as your variance. When the error rate has a high value, we call it high variance. When it is having a low rate, we call it as a low variance. Underfitting. This is a statistical model or a machine learning algorithm. Or say your statistical model or a machine learning algorithm is said to have a underfitting when it cannot capture the underlying trend of the data. That is, it only performs well on your training data. Only on your training data. But it performs poorly on your testing data. So if I were to give a funny example of that, it is nothing but, just like trying an oversized pants. Oversized pants or a dress, you can say. Underfitting, what happens is it destroys the accuracy of your machine learning model. And if it occurs, then its occurrence simply means that our model or the algorithm does not fit the data. Yeah, it does not fit that. Now, this usually happens when we have fewer data to build an accurate model. And also when we try to build a linear model with a few non-linear data. In such cases, what happens, the rules of your machine learning model are too easy and flexible also to be applied on such minimal data. And therefore, the model will probably make a lot of wrong predictions. Underfitting can be avoided by using what? If we use, say, more data, then we can reduce our underfitting. When you have high bias or low variance, the size of your training data is that you are using is not enough. The model is, say, too simple, or your training data is not clean and also containing a lot of noises. These are the reasons of your underfitting. Techniques, you can say, you can increase your model complexity, increase the number of features, remove the noise from the data, increase the number of epochs, or increase the duration of your training to get the better. That is about your underfitting. Talking about overfitting. a statistical model is said to be overfitted when the model does not make accurate predictions on your testing data. When a model gets trained with so much data, it starts learning from the noise and inaccurate data. So whatever you are having in your data. And when testing with test data results in your high variance, then the model does not categorizes the data correctly because of too many details and noise. The cause of overfitting are non-parametric and non-linear method trends. Because of these types of machine learning algorithm, we have more freedom in building the model based on the data set. And therefore, they can really build unrealistic models. Now, the solution to avoid overfitting is using a linear algorithm. If we have linear data, or using the parameters like your maximal depth, if we are using your, say, decision. If I were to summarize it, overfitting is a problem where the evaluation of the machine learning algorithm from the data set is different from your unseen. So when you are having high variance and low bias, or your model is too complex, or your size of the training data set is huge, then you end into overfitting of V. So here, if you see, we are having high bias over. That is, underfitting is actually occurring over. But when you see over here, we are having appropriate fitting. This is something very actual. And here, if you observe, here we are observing your overfitting. This is your overfitting. Overfitting is nothing but your too good to be true. How do you overcome this overfitting thing? You increase your training data, reduce your model complexity. Early stopping during the training phase, regularization, lasso ridge regularization. Use dropout for your neural networks to tackle your overfitting. All these various things you can use, or tools or tricks you can use when you want to deal with your overfit. The same thing that I have told you, the same thing is overfitting, underfitting, same difference. A statistical model is said to be overfitted when we train it with a lot of data. When a model gets trained with so much data, it starts learning from the noise and inaccurate data entries in your data set. Then the model does not categorize the data correctly because of too many details. Whereas underfitting, a statistical model or machine learning algorithm is said to have underfitting when it cannot capture the underlying trend of the data. Underfitting destroys the accuracy of your machine learning model. Its occurrence model simply means that your model or the algorithm does not fit the data well in. So guys, this is all we wanted to discuss about our CRISP MLQ. And I am going to stop the session for today over here. Tomorrow, talking about our domain analytics, tomorrow we will be discussing upon, let me quickly tell you, okay, so tomorrow we will be discussing about EDA, exploratory data analysis, or your people. So what we will do, we are going to take a data set related to our sports analytics, and we are going to perform the EDA. We can use either Jupyter or we can also use your spider. So tomorrow we are going to do this related to our sports analyst. Okay. So guys, thank you so much for joining the session today. I hope it would be, a learning experience for you people. So all the best. Keep on practicing, guys. We'll be meeting tomorrow again. Be safe, have fun. See you tomorrow, guys. Thank you so much for joining.